Okay, good morning, everybody. It's nice to be back in the United States. Today's topic is approximation algorithms, which is a topic I like very much. It's also like a very popular topic these days. It's at the sort of forefront of research in theoretical computer science, algorithms, theory, and complexity. It's also nice, it's kind of a positive lecture after our last lecture is a bit of a downer lecture where we showed all sorts of problems were probably very hard to solve efficiently. Actually, you might remember the names of some of these problems. I think we've talked about all of them either in last lecture or previous lecture. So these are all the names of algorithms problems that are, pretty natural algorithms problems that you want to try to solve. So I'll remind you a little bit of some of the definitions. Like SAT is the problem where you're given a Boolean formula and you want to decide if there's an assignment that's to the variables that satisfies the formula. 3-SAT is the same thing, but the formula's got a special form where it's just a big and of a bunch of ors, each or having 3 variables or negated variables. Vertex-Cover is a problem we'll talk about a lot today. There you're given a graph G and a number K. And you're trying to find if there are some, at most K vertices that touch all the edges of the graph. Clique is another one. Max cut is like my favorite problem. There you're given a graph and you have to give the vertices 2 different colors. And you're trying to get as many edges cut as you can, where cut means that the vertices at its endpoints have different colors. And Hamiltonian cycle is another nice one. You're given a graph and you want to know, is there a cycle that goes through all the vertices and touches them, each vertex exactly once? Okay, so these are all great problems. Unfortunately, last time as we saw, SAT has this property that it's NP complete, which in particular means that it's solvable by a polynomial time algorithm if and only if every problem in NP, of which there are quite a lot, is solvable by a polynomial time algorithm. And most people kind of believe that that's not true, which in particular means they don't think SAT can be solved by a polynomial time algorithm, which is a shame. Then we looked at 3-SAT, which is easier because it's like a special case of SAT, but even that's NP complete. And Vertex-Cover is NP complete. Finding the largest clique in a graph is NP complete. I don't think we saw this one, but it's true that deciding if a graph has a cut of a certain size, at least a certain size, is NP complete. Deciding if a graph is Hamiltonian cycle is also NP complete. So basically it was like a sad story, like we invented this beautiful theory of algorithmic complexity. We had all these nice problems. We defined our model of algorithms in polynomial time. And then it turned out like everything is NP complete and like we probably cannot solve it efficiently. So that's kind of a bummer. So if there's only sort of one idea in this lecture, which is that, it's like a positive idea. You should just not give up. You should not just cry and say, well, everything is NP complete. I can't write an efficient algorithm for all these problems I want to solve. I'll just give up. No, you should keep trying. So what does that mean? You should keep trying. What can we do? So let's take Vertex-Cover. That's a nice problem. That's kind of an example. It's an NP complete problem. I'll remind you of it even in more detail. So the input to the problem has 2 parts. There's a graph. That's part of the input. And another part of the input is just a number, k. And you're trying to decide if there's a vertex cover of size k. Now, vertex cover is a technical term. It's a funny term. A vertex cover is a set of vertices, S, such that every edge touches at least one of the vertices in S. You've got to cover all the edges. It's called the vertex cover. Okay, so you're trying to find if there's a small size, at most size k, set of vertices that touch all the edges. So here's an example, like maybe here's G. And let's figure out what is the smallest vertex cover in this graph. So here I highlighted 3 vertices, these yellow ones. And if that's our set S, then that's a valid vertex cover. That's an acceptable solution, because if you check, every single one of these white edges touches at least one yellow vertex. So the size of this vertex cover is 3. Now generally you're interested in trying to make a vertex cover which is as small as possible. So in this graph, do you think you can get a vertex cover of size 2? Yes? Okay, so if you think it's yes, you should just say, like, what is the vertex cover? So do you have a suggestion?
Yeah, just remove the bottom one.
Remove this one?
Yeah.
Then you missed this edge.
Missed the edge.
Yeah. Okay. Anybody say no? Yeah, the answer is actually no, but then that's a little tricky. How could you easily convince me that there's no way to cover all the edges with 2 vertices? So I'll ask you in a second, but one way you could do it is you could just be, there's like 7 vertices, right? So if you get 2 of them, well, there's 7 choose 2, which is 21 possibilities. So you could just be like, well, this possibility doesn't work, this one doesn't work, this one doesn't work. That would take you 21 steps. But maybe there's like a slicker way to do it. Can anybody sort of give a short explanation why 2 won't work? Somebody, back there?
There's the triangle, and the triangle needs 2, and then there's the line on the left, which needs at least 1.
This triangle needs at least 2. Yeah, that's true. And then this one needs at least 1. Yeah, how do you know you couldn't have like, well, that would prove that you need at least 2. Oh yeah, 2 for, okay, good. 2 for the triangle and 1 for that. Yeah, that's a good explanation. Yeah?
There are 8 edges.
Yeah.
If we had 2 vertices and then we could cover at least 4.
Well, this vertex could cover 3. Yeah. Okay, this guy covers 4 edges, right?
Yeah.
So
2 vertices that cover.
that's right. Yeah. There's a few ways to do it. This guy covers 4 edges. He's the maximum. So the best you could do 8, but maybe the second one is 3. Here's another way. I mean, these are all perfectly valid and good ideas. Here's another way that you can see it. I bring up this way because I'll mention it again later. It's like I say, take a look at these 3 yellow edges. This is similar to what you said. Take a look at these 3 yellow edges. They form a matching because they don't share any vertices in common. And you can tell, I mean, if you have a matching, then you need at least 1 vertex per edge in the matching because there's no cost sharing possible. They don't touch anything. So you need at least 1 guy from here, 1 guy from this edge, 1 guy from this edge, so you need at least 3. It's just yet another way to see the same thing. Okay, so for us, this graph of size 7, it wasn't too hard to figure out the smallest vertex cover. But if I give you a graph with 10 million nodes, and I give you k is I don't know 1,000, and I say, is it possible to choose 1,000 nodes out of these 10 million nodes that covers all the edges? It's not so easy. Indeed, it's sort of reflected in the fact that vertex cover is NP-complete, which doesn't guarantee that there's no polynomial time algorithm for it, but it does if p does not equal NP. But our motivation in this lecture, right, is we should not give up. So let's take a little bit more of a closer look at exactly what this statement means, vertex cover is NP-complete. Well, this is not identical to the statement that it's NP-complete, but this is a consequence of it being NP-complete. Since it's NP-complete, we know that if you assume p does not equal NP, which most people do, then there's no algorithm that runs in polynomial time and which, for every single graph G, always finds the minimum size vertex cover. Because if there were such an algorithm, then given a graph G and a number k, you just find the minimum vertex cover in G in polynomial time and see if that's less than or equal to k. And then you would have solved the vertex cover problem. And then, since it's NP-complete, p would equal NP. So the idea here is, okay, we have to accept that this is true, but maybe we can still get some, positive news out of here by, I don't know, varying or weakening this statement in various ways. And in particular, for all these yellow phrases here, maybe if we change them a little bit, we can still get something good. So let's look at them one by one. The first one is, we're assuming the algorithm runs in polynomial time. Well, that's usually something that you hope for with an algorithm, but you could relax that if you wanted. For example, there's a field that studies sub-exponential time algorithms, which basically means algorithms that run not as slowly as the total naive brute force. The total naive brute force algorithm for vertex cover, you could just try all possible subsets of the vertices, of which there are 2 to the n, and just see if each one is a vertex cover. That's a polynomial time check. And then pick out the smallest one. So that's the ultimate brute force algorithm, takes 2 to the n time, and that's not very good. If n is maybe n is 20, it's okay, but if n is 100, it's not okay. But you could try to do better than this. Probably you're not going to get it down to polynomial time, like n to a power, but maybe you could get it down to 1.5 to the n time, or 1.1 to the n time. That would be actually pretty good. I mean, if it's 1.1 to the n time, probably you could, do it on a graph with n equals 100 vertices. Or 2 to the n to the 0.1 time. Actually, that would be pretty great. This you could probably do I don't know, you could probably plug in a pretty large value for n and get a reasonable number of steps there. So, maybe this is not the dream algorithmic solution, but it wouldn't be so bad. And this is actually not just a complete fantasy. For example, the latest and greatest for this particular problem, vertex cover, comes from 2010, not that long ago. And there is an algorithm that, just given any graph, finds the smallest vertex cover exactly in time 1.28 to the n. Okay, and maybe next year they'll get it down to 1.27, and you could actually maybe use this algorithm if n is like 100. Not if n is 10 million, but it's good to know about. Okay, so that's one angle you could try to pursue if you're interested in not giving up. Let's look at this next possibility, all graphs. So maybe you want to give up on this. Vary this. So you might want to find an efficient algorithm that always finds the smallest vertex cover, but maybe it doesn't work for all graphs. For example, you could try to get an algorithm that works in certain special cases. So for example, maybe you could find an algorithm that always finds the minimum vertex cover in a tree. Actually, that's not too hard. You should think about how to do that. There's an easy polynomial time algorithm for that. It's also true that in polynomial time, you can find the smallest vertex cover in any bipartite graph. That one's harder, but it's known how to do it. It's also true you can find the smallest vertex cover in any series parallel graph. I'm not going to define what that is, but it's a special family of graphs that's sort of more general than trees. Well, if you know those like physics circuit things with the parallel and the series, it's like graphs that look like that. Okay, so actually there's lots of families, like kinds of graphs, where we actually do know an efficient algorithm to find the smallest vertex cover of them. And then maybe if you're actually trying to solve this on some graph that's coming in, maybe it'll be one of these families, and you can do it. You might even try to find an algorithm that works for all graphs that are encountered in practice. It's a little hard to say what that means. So it's not exactly a scientific statement. What does it mean for a graph to be encountered in practice? But you could still try to find an algorithm that seems to work. You'll have maybe a hard time proving that it works for all graphs that it encounters in practice, because there's not a definition for that. But it's a reasonable try. OK. And the third thing that maybe you want to change is this statement that you're finding the minimum size vertex cover. And that's actually what we're going to talk about for the rest of the lecture. This is sort of the topic of approximation algorithms. You're finding like an approximately best solution. And in this framework, we don't give up on polynomial time. You have to have a polynomial time algorithm. And we don't give up on working for all graphs. Your algorithm should have the right properties for every single input graph. But we just relax the concept that you have to find the minimum size vertex cover, like literally the smallest one. Maybe you only have to find one that's pretty small. If I could give you an algorithm that ran in polynomial time, and for every single graph it found a vertex cover that was at most 1% bigger than the optimal vertex cover, you'd probably be pretty happy with that. Okay, and that's not ruled out as far as we know. So that's the thing we're going to think about now. Okay, approximation algorithm is always, well, in this case, it's about trying to find pretty small vertex covers in polynomial time for all graphs. Or for other kinds of problems, like finding the largest clique in a graph. Maybe we're going to relax the requirement that you find the largest clique. You have to just find a pretty large clique. And in fact, this is possible. It depends quantitatively on what you're shooting for, but sometimes this can be done. So here's a result from 40 years ago due to a guy called Gavril. And we'll see the proof of this later, but I'm just putting it up now so that you can see it. He showed there's a polynomial time algorithm. Actually, it's a very simple algorithm that given any graph at all, G, it always outputs a vertex cover. So it always outputs a set of vertices that's valid that touch all edges. It's not necessarily the smallest vertex cover, but he guarantees, he proves that its size is at most 2 times the size of the smallest vertex cover. Okay? And this is called a factor 2 approximation for vertex cover in the jargon. We don't need to use the jargon. We can just say this is what it is. And that's pretty good. Maybe if you have a 1,000,000 node graph, the smallest vertex cover is of size, 105. He'll give you a vertex cover for sure. That's at size at most 210. So not bad. OK, any questions about this so far? We'll see how to do this later in the class. Let me show you another example. This is from, you'll have to remember a little bit something from lecture 10, which was the first algorithm about graphs. And at the end, we talked about this max cut problem, which is my personal favorite algorithms problem. And I'll remind you what it is. This is the one that was illustrated with some castaways from Survivor. Okay, so the input in max cut problem is a graph. Here's a little example. And what is the output? The output is you're allowed to output any two coloring of the graph. You're like supposed to split the two vertices into two tribes, maybe the blue one and the yellow one. And what are you trying to do? You're trying to get as many of the edges cut as possible, or we say an edge is cut if its two vertices have different colors. So here's a potential solution. The color of these ones yellow, these two blue. And here we've cut 5 out of the 6 edges. All the yellow edges or orange edges are cut because they go between different colors. Only this one is not cut. We got only 5 out of 6. Now if our algorithm outputted this, we would actually say you did the perfect job. Congratulations. Because actually it's not possible to do a 2 coloring that cuts all the edges here. Can somebody say why not? I'll ask you because you're the triangle guy. Or maybe it was you. Yeah. OK, this is the triangle corner of the room. Thanks. Yeah, there's a triangle here. And you can just tell whenever you have a triangle, no matter what you do, you're never going to cut all 3 of the edges. You'll always have 2 vertices of the same color. I guess that's a super baby version of the pigeonhole principle. OK. Now, here is the truth. Unfortunately, give the problem task of given a graph, find the maximum cut, find the coloring that cuts the most possible edges, is NP hard. If you could do that in polynomial time, then you could solve every NP problem in polynomial time. However, at the end of that graphs lecture, lecture 10, we saw an interesting algorithm for trying to find a good cut called local search algorithm. It's a very simple algorithm. It's polynomial time. Basically, it just started with any 2 coloring at all. And then you just kept going through the vertices. And you say to yourself, if I change this vertex's color from blue to yellow or yellow to blue, would that increase the number of cut edges? And if it does, you're like, I'll do it. And then you just kept doing that until no single vertex color flop would give you a new edge. And that didn't always find the best coloring. It didn't always cut the maximum number of edges. But we did show then that it always cuts at least half of all the edges. And in particular, the number of edges cut by local search, it's at least half of all the edges. And certainly that's at least half of the number of edges cut by the best solution. The best solution, you can't always achieve it, but it's never going to be more than all of the edges. So this guaranteed that the solution we got here was always at least half of the best solution. Unlike Vertex-Cover, this is a maximization problem where we're happier the bigger the answer is. Okay, so here, that's why this number is less than 1. It's, we got at least half of the solution. And we call this a factor half approximation algorithm for max cuts. So that's another algorithm where, I guess in some sense, in both problems, we're within a factor of 2 of the best solution. OK, so this is just to illustrate that sometimes it is possible to have a polynomial time algorithm that has a good guarantee for every single graph. It doesn't always find the best solution, but it always finds a solution which is within some factor of the best solution. The closer that factor is to 1, the happier you are. By the way, that's not the best known approximation algorithm for max cut. In the mid-90s, these 2 people, Gomans and Williamson, gave a different polynomial time algorithm that is better than a half factor. It actually always finds you a cut whose size is at least 0.87856 times the biggest cut. And this is a very beautiful algorithm. I love it very much. It's part of the reason why max cut is one of my favorite problems, my favorite problem. But it's quite difficult to explain this algorithm. It uses a lot of geometry and some crazy ideas. But it's a great algorithm. So, that's pretty good, actually. You're always going to cut that's like, basically 88% as large as the optimum. Yep. Oh, this is actually, it has something to do with geometry. There's like spheres involved in this algorithm, or circles. And this is like tan theta over 2, where theta is some other number. No, it's like 1 over sine theta, where theta is the solution of some trigonometric equation. So it's actually like 8, 7, 8, 5, 6, 2, 3. It's like some presumably irrational number. That's kind of crazy even that such a crazy number could arise in such a simple problem. OK. OK, so the rest of the talk, the rest of the lecture, I'm going to tell you more about approximation algorithms. I have to devote one slide to like a little technicality, just because I feel like I should only say things that are, strictly speaking, true. And this is about it's a technicality about notation or terminology, optimization versus decision. So what do I mean by this? So if you recall, NP is defined to be a class of decision problems, a class of languages. And that's because, this whole story, starting from automata and Turing machines, we really like to focus on decision problems because it's simple. Decision problems, yes-no problems. So like all these things like 3SAT, it was a yes-no question. Given a 3C and a formula, is it satisfiable? Or, given a Hamiltonian cycle, given a graph, is there a tour that touches all the vertices exactly once? And that's quite natural. But there are the ones where it's a little bit unnatural, right? Like for Vertex-Cover, we didn't just say, like, given a graph, find the smallest Vertex-Cover, right? For some reason, we kind of artificially made it into a yes-no question by having this k. We said, like, given a g and a number k, are there k vertices which touch all the edges? And we did that similarly for, like, max cut. We had this k. So that it would become a yes or no question. And, those yes or no questions are easier to think about when you're studying NP. That's for technical convenience. But for a lot of these questions, maybe even almost all these questions, there's a non-decision version of the problem, an optimization version of the problem, which is a bit more natural. Like, for example, with Vertex-Cover, it's more natural to just say, like, find and output the smallest Vertex-Cover. Or, for maxcut, find and output the two coloring that cuts the most edges. Okay, so it's not a decision problem. Even for things like 3SAT, you could say find the truth assignment that satisfies as many of the clauses, those little size 3 ors, as you can. Or for like Hamiltonian cycle, which is about is there a tour that passes through all the vertices once, the optimization version of that is called TSP, traveling salesperson problem. And it's like given a graph G where there are costs on the edges, find the cheapest tour that touches all the vertices once. So these are like a bit more natural, the optimization version of the problem, but they cannot be in NP because they're not decision problems. NP is defined to be a class of decision problems. So that's the technicality. But you can still say that these problems are NP hard, and that just means, like finding the smallest vertex cover in a graph is NP hard. It means if you could solve that problem in polynomial time, then you could solve any NP problem in polynomial time. Okay, so we'll call these problems NP hard, but we can't call them NP complete because they're not decision problems. But basically, this is a terminology technicality, which I didn't want to get too hung up on, but I also didn't want to hide from you. Okay, any questions about that? Mm-hmm?
It's not related here, but the sort of reverse holds, like if you could solve the decision version, can you solve this?
Yeah, that's a great question. If you can solve the decision problem, can you solve this? So let's think about Vertex-Cover. One thing that's easy to see is that suppose you can decide the decision version of Vertex-Cover. I give you a k, and I want to know, is there a Vertex-Cover of size k? If you could always do that, then you could sort of solve this version. You could find the size of the smallest Vertex-Cover, because you just try k equals 1, k equals 2, k equals 3 until you got a yes answer. It's not clear. Okay, now once you know that the size of the smallest Vertex-Cover is like 100, how do you actually find that Vertex-Cover of size 100? This you also can do efficiently, just with the ability to solve the decision problem. It takes a little bit of thought. So I'm not sure if we have any problems like that on the homework, but you can do it. You have to do things like, I'll take the graph and I'll take away this edge, or I'll take away this vertex, and now ask your decision question about that. And somehow the answer will tell you if this vertex was key to that smallest Vertex-Cover. Yep. The question was, does it imply that if you can solve, so all this theory of NP completeness was about if you can solve the decision version of this problem, like 3SAT, you can solve the decision version of Vertex-Cover, let's say, and vice versa. What about, is that also true that the optimization problems are equivalent? Not necessarily. So it's kind of for each problem, you sort of need to check whether the decision problem can be reduced to the, whether the optimization problem can be reduced to the decision problem. Whether you could solve the optimization problem if you could solve the decision problem. That's almost always true, but sometimes requires a little bit of thought. So it is true for all of these problems that if you can solve the optimization version of any one of these problems, you can solve the optimization version of any of the other ones. Okay. Any other questions? OK, so we'll talk about the optimization version in the rest of the class because it's a bit more natural. OK. OK. So, the theory of NP hardness that we talked about was sort of, the main punchline of it was we had this huge class of problems, the NP complete problems. And they're all kind of, it seems like they're equivalent. Like, if you can solve one of them in polynomial time, then you can solve all of them in polynomial time. So they're all solvable efficiently, or none of them is solvable efficiently. So sort of the takeaway from that story is that, they're all equally hard. But that's true if you want to talk about solving them exactly. But if you start to talk about solving them approximately, then actually they're quite different. Like each problem is like its own little snowflake where it has like a different story on how hard it is to come up with pretty good solutions to it. So instead of just saying shutting the door and saying all these problems are equally hard, they're all probably hard. Each problem goes back to having the status of, OK, we've got to think about it. We've got to try to come up with the best algorithm we can from the point of view of finding approximately optimal solutions. So today is going to be kind of just a little case study to show you about this. There's not really much theory in it. It's just some examples. And we'll see 3 different approximation algorithms. We'll see a somewhat good approximation algorithm for the Vertex-Cover problem, a pretty good approximation algorithm for a problem that we haven't talked about yet, but I'll define it, called K-coverage, and some very good approximation algorithms for this TSP, traveling salesperson problem. Okay, so it's kind of a lecture of examples. So let's start with Vertex-Cover. OK, so let's remember Vertex-Cover. You're given a graph G, and now we're just going to think about the optimization version where you're trying to output a Vertex-Cover which is as small as possible. So remember, you always have to output a set of vertices that touches all the edges. You're not trying to find some vertices that touch most of the edges. You have to find a set of vertices that touches all of the edges. But what you have some leeway on is the size. You don't have to find the smallest possible such set, just a pretty small such set. So let's say I said, I know that Vertex-Cover is NP hard, but nevertheless, you have to write a Vertex-Cover algorithm. I give you 3 minutes to think about how you're going to do it, put you in a room, go. You'd be like, well, I don't know what to do. But probably the first thing I think any of you would do would be this algorithm, which is what you might call the greedy algorithm. Greedy algorithms is a very interesting class of algorithms. It's a very powerful class of algorithms that gets used all over in the study of algorithms. It's basically you just always make the best seeming choice at the instant and hope that works out for you in the end. And it's very natural. So this is what I think the greedy algorithm would be for the Vertex-Cover problem. You're given a graph G. You're trying to build up a Vertex-Cover. You've got to cover all the edges using vertices. So you start your Vertex-Cover as the empty set. And then you do a loop where you say, well, as long as there's some edges I haven't covered yet, I'm not done. And so this is the greedy step. You just go through all the vertices and pick out the one that covers the most edges that you haven't covered yet. So for example, in the beginning step, you would pick the vertex with the largest degree because it touches the most edges. Okay, and then you would include that into your Vertex-Cover, your partial Vertex-Cover, irrevocably. You're never going to change your mind. And then now that you've included it, that covers all the edges that it touches. And then you keep going. Okay, you keep doing that until you have enough vertices that all the edges get covered. Does that make sense? So I'll give you an example. Let's see it on this nice graph. OK, right here in yellow, I've written the number of edges that each vertex covers. And it's just the degree here. So the greedy algorithm will start out by taking the largest degree vertex, this guy that covers 4 edges. And then it'll keep that, and it'll also mark, with a check mark, all these edges as they're already covered. I don't have to worry about them now. And then actually it'll revise its opinion on how many edges are sort of newly covered by each vertex. So for example, this one, now it covers 0 new edges if we were to take it, so forget it. This one touches 3 edges, but one of them is already covered, so we only count it for 2. Okay, and so forth. So it figures that out. That's easy to do. And now it picks the one that's covering the most new edges. Now here actually there's some ties. You have 3 choices. So we didn't exactly specify what it does. Let's just break ties arbitrarily. So let's say it chooses this one next. So then having chosen that one, it marks the 2 edges that it covers. It sort of revises the story on how many new edges each vertex covers. Now it comes to the 3rd iteration of the loop. This person is still covering 2 edges that haven't been covered yet, and that's the best, so we'll take it. mark the edges that it covers. And now everything is zeros. We've covered all the edges, and we're done. And the greedy algorithm outputs this set S with 3 vertices. OK, so it's done. And here, everything looks great. It actually found a vertex cover of size 3, and we previously argued that that's the best, smallest vertex cover in this graph. So it found the optimal solution. It's quite good. So let's talk about how we analyze this algorithm. And when you're analyzing approximation algorithms, there's always 3 things to think about: correctness, running time, and solution quality. So correctness means it should always output a vertex cover. It's supposed to always output a set of vertices that touches all the edges. And that's clear that it'll do that because it keeps going until it covers all the edges. The running time, this algorithm is polynomial time. And for the purposes of this class and a lot of the time in 251, that's good enough for us. I mean, you could try to analyze it. You know, it does a loop. And each time it does the loop, it adds at least one more vertex into its set. There are only n vertices, so the loop will only go at most n times. Inside the loop, it has to sort of look through all the vertices to find the ones that covers the most edges. Maybe this will take m time or something. But anyway, it'll run in polynomial time. OK, so we won't focus on the exact running time too much. We'll just be happy with that. Now, what about the solution quality? This is the interesting question. So I claim there must be some graph G, there must exist like in a specific graph G, where the greedy algorithm does not find the smallest vertex cover. I'm very confident that such a G exists. Can somebody say why I'm so confident? Outside of the triangle corner? Somebody over here? Yeah? Yeah. Otherwise, if there were no such graph, then you'd be like, that means by definition, the greedy algorithm finds the smallest vertex cover, which, as we know, since vertex cover is NP hard, implies P equals NP, and that would be a very surprising outcome. So probably such a G has to exist. And in fact, if I gave you 5 minutes, you would probably find a graph like this one, where greedy does not find the best solution. So here's a bad graph for the greedy algorithm. So what is the size of the smallest vertex cover in this graph? 3, that's right. If you take this vertex, and this vertex, it touches all the edges. OK, and that's the best. But what will greedy do? What vertex will greedy choose first? Yeah, it'll say, ooh, this one covers 3 edges. Everybody else only covers 2 or 1. I'll choose that. And then once it takes it, well, it covers these 3 edges, but it still has these 3 to go. And it has to spend like 1 vertex for each of them. So maybe it'll do this, and it finds not the best solution. It finds a solution of size 4. OK, so greedy does not always work perfectly. In fact, you can say a bit more. You can even conclude from this that the greedy algorithm is not a 1.33 factor approximation algorithm. Why do I say that? Well, if it were a 1.33 approximation algorithm, that means whatever the optimal solution is, greedy is only going to give you a solution that's at most 1.33 times as big. But that's not true. Here on this graph, the optimal solution is size 3. 3 times 1.33 is 3.99. But greedy actually gives you a solution of size 4. OK, so it's not only is it not a perfect algorithm, it's not even a factor 1.33 approximation. OK, now you might say, well, that was one bad graph, but maybe that's the worst it gets. But it's not true. There's a worse graph for greedy. It looks like this. All right, so well, let's have you think about it. What is the size of the smallest vertex cover in this graph? Actually, the first question is, how many vertices are in this graph? Well, you can work on that while I open Piazza. All right, so what is it? OK, you guys do the hard work. I'm going to count the number of vertices. 33? Yeah, 24, 27, 31, 30. Yeah, 33. All right, so think about it. How many people have voted? Put up your hand. Okay, a lot of people have voted. Well, let's see what you think. Ooh. Yeah, everybody is going for 12. That is the correct answer. Congratulations. I'm closing it. Okay. Yeah, it's 12. It's these guys right here. I mean, if you study carefully, those 12 touch all the edges. But Greedy is not going to find that. Greedy is going to look at this graph and say, ooh, this vertex cover is 6. Like, I'm going to take it. And this guy covers 6. I'm going to take it. And then actually, once it's taken these two, it'll actually go for these people that cover 4. And then once it takes those, it'll actually go for these ones that cover 3. Because for example, this person originally covered 1, 2, 3, 4. But once you take this degree 6 guy, it only covers 3 new ones. So at first it was pretty good, but once you choose this one is looking better. And it's kind of set up to like do that, right? Sort of foil the greedy algorithm. So if you check it out, greedy will actually do this, which is 21. Okay, and 21 over 12 is like 7 over 4. That's 1 3/4. So you could say that greedy doesn't even achieve a 1.74 approximation because 1.74 times 12 is actually less than 21. Yep.
I guess if you keep adding vertices like this with edges, and you can show that it's not any approximation?
It's not clear. I mean, you should, well, in fact, there are worse graphs for greedy, it's true. And that would also be a good homework problem. Find a graph where the ratio is even worse than 17 over 12. I mean, you have to be kind of clever to, figure out what I did in this graph and try to extend the idea behind it. But if you figure out what I did there and sort of extend the idea behind it, you'll actually, sort of the next tricky graph in that family will show that it's not even a 2.08 approximation. And it's actually not even a 3.14 approximation. It's not even a 42 approximation. It's not even a 999 approximation. So what does this mean? It means there's some graph out there, like a very specific graph, where the smallest vertex cover has this size, but when you run greedy, the size of the vertex covered outputs is like 1,000 times bigger than the optimal size. So it's like what you were saying. It's quite bad, actually. In fact, you can prove, this is not too hard, for every number C, like 42, 999, a million, it's not a C approximation. There's some graph, depending on C, such that the size of the vertex cover greedy outputs is more than a C factor times as large as the minimum size. Yep?
Can you prove anything about like the average case that it's okay or something?
It's a good question. The question is, can you prove that like maybe if somehow for an average case or a typical graph it's okay? One thing you need to do if you want to prove something like that is you have to define exactly what you mean by an average graph. There are notions of like how to take an average graph. Like you could literally look at all graphs on n vertices and take the average sort of performance ratio over all of them. And actually that will probably be pretty good. Then you have to debate whether or not you really feel that's like a good way to like measure things, but maybe. I think it's probably true that in practice, I mean, like this graph is pretty carefully designed. Like if you just have some graph that actually represents something in the real world, it's unlikely to be literally exactly this graph. So it could be the case that the greedy algorithm often works well, but it does not provably always work within a constant factor. Okay, now if you remember this person, Gavril from 1976, he kind of came to the rescue. He had a different algorithm. It's not the greedy algorithm that does better. It's a very simple algorithm, and it starts the same. This is a new algorithm. It's going to fit inside this box. You start with your vertex cover being the empty set, and you're going to add vertices to it until you've covered all the edges. So the greedy algorithm looked at all the vertices to find the one that covered the most. Gavril starts by looking at the edges. And in fact, you can this step is a little non-deterministic. You can just take any unmarked edge. Just take any edge you haven't covered so far with vertices v and w. Now, you got to cover this eventually, so you need to add either v or w into your vertex cover at some point. So which one does Gavril add? He adds both of them. Now that seems like a crazy move, because you only need one of them, so why would you add both of them? This question mark is a little bit like in like chess. Like I don't play chess at all. I'm terrible at it. I like know the rules, but sometimes I like reading about it, even though I don't know anything about it. It's like sometimes I also read the recaps of TV shows that I don't actually watch. But this is like notation they use in chess to denote like a questionable move, like a bad move. But actually, we should put an exclamation mark because this is actually a great move. It's very surprising, but it's very smart. That's it. That's the whole algorithm. So he's going to add both of them in. And then, OK, now that we have v and w, we may as well mark all the edges as covered that they touch. And then you just keep going. You pick some other edge that you haven't covered yet and repeat and add both its vertices to your set. Now that looks strange, but let's see why it's actually not such a bad idea. Although first I'll do an example which will make it seem like a bit of a bad idea. So let's take this graph that we've always been using and see how Gavril would work on it. So it first starts by choosing some edge, let's say this one. And then it adds both its endpoints into the set. Yeah, you're not happy about this, huh? Well, that's what it does. And then it marks all the edges that it's covered. It's kind of pointless to have used on this one, but whatever. Then it takes another edge it hasn't covered, maybe this one. Takes both the vertices. This looks terrible so far. Marks all the edges that they cover. It takes another edge that hasn't been covered, let's say this one. Takes both the vertices. Marks all the edges that they cover, and now it's done. And now it's like, great, I covered all the edges. I have a vertex cover, the yellow vertices. It's of size 6. The smallest was 3. So right away we know the best possible thing Gavril could be is a factor 2 approximation. Because already there's a little graph where it's giving you something 2 times as bad as the best. But that's the theorem. This algorithm will never be worse than 2 times as the smallest. And the proof is going to fit on this slide. OK, so how does the proof go? So let's imagine this Gavril algorithm. And let's say the overall loop goes t times. Then what is the size of the vertex cover output at the end? 2t, right? Because every single iteration, it takes both vertices in the edge, exactly 2 new vertices. So it puts 2t vertices into its set. OK, so let's just give names to the edges it picked. Let's just call them E1 up through ET. So that's E1, E2, E3 in our example. And here's the key claim. We claim that it always chooses edges which form a matching. Do you have a question?
Do we have to say it's less than or equal to 2t?
I think it's always exactly 2t.
If you had a path of just 3 vertices and that's your entire graph,
Yeah.
then you're going to pick all 3, but you're going to have 2 iterations, right?
No, it'll have 1 iteration. Because let's say it'll pick one edge. It'll take.
But
Yep.
is there any case where
No, it only chooses. Well, that kind of actually enters into this claim, which is that it only adds vertices. Like it never tries to add the same vertex twice. Because in particular, once it adds a vertex, it marks all the edges as covered that it touches. And so then it'll never choose that subsequently. So this is actually kind of proving this statement. Right? Like when you choose a edge, ej, you only choose it because it's unmarked. Which means that you hadn't already chosen its endpoints. Like if this is E2, by the virtue of the fact that we chose it in the loop, that means these 2 were never chosen before. So that means they're not among the endpoints of the edges we've already chosen so far. So every time you consider a new edge, it has to be disjoint from all the edges that you considered in the past. Otherwise, it would have already been covered. Because you take both vertices of the edge. OK, and now we use this observation we said before. Whatever these edges are, E1 through ET, they form a matching, which means any vertex cover at all has to have at least 1 vertex for each of these edges. There's no way you can have a vertex cover unless you have each edge in a matching has at least 1 vertex. They don't share any vertices, so you can't get any savings. So in particular, the minimum size vertex cover, S star, I have no idea what it is, but whatever it is, it has to have at least 1 vertex from each of these EJs. Just because it is a vertex cover. So its size has to be at least t. Okay, so for Gavril's final vertex cover set S, its size is 2 times t. And the size of the smallest vertex cover is at least t. So we have that the size of S is at most 2 times the size of the smallest vertex cover. Okay, and that's what we mean when we say Gavril is a factor 2 approximation. Okay. Any questions about that? Yeah?
Can you explain why this is matching? The reason why it's matching?
Yeah, let's go back to that. So what I'm really going to explain, I mean, this goes a little bit fast, is that every time it considers a new edge, ej, that ej will have no vertices in common with any of the edges it previously considered. And that actually means it's a matching because, so you have to think about that for a little bit, because if each edge has no edges in common with the previous, sorry, has no vertices in common with the previous edges, then like none of the edges ever have any vertices in common. So that's a little deduction you have to think about. And then the reason that's true is when you consider, let's say, the second edge, none of these vertices could have touched a previous edge you consider, because whenever you consider an edge previously, you include both its endpoints into your set, and you mark as covered all the edges that they touch. So like this guy, if he somehow touched one of these 2 vertices, then he would have been marked as covered earlier, and so you wouldn't have chosen him later. That takes a little thinking about. Okay, good. Okay, so you should think about this in the privacy of your own home if it went a little fast. Okay, so that's actually all I'm going to say about vertex cover, and I showed you a pretty good approximation algorithm for it. Okay, now I'm going to tell you about an approximation algorithm for this k-coverage problem. So what is the k-coverage problem? It has a very austere name. I was trying to think of a good way to explain it, and I thought it might be better explained as the Pokémon-Coverage problem. Now, I'm actually an old man. I'm actually too old to really know about Pokemon, like it's after my time. But I have like a 6-year-old son who is, I guess going to get involved in Pokemon. So I'm trying to find out about it. So this is the story I'm going to tell you. It's an algorithms problem. So let's say there's some Pokemon. I don't know, like Bulbasaur or something? Is that one of them? It's got the cards. OK. And you got some trainers. And like each trainer has a subset, like owns a subset of the Pokemon. Maybe like this. OK, so like this is, who is this? Ash. OK, that one I knew. Ash has these 3. And like this person has these 3, and this person has these 2, etc. And furthermore, you're given a number k. So this is an algorithms problem. You're given, yes, it's very photo worthy. It's going to be on the slides though. So the input to this problem is like this picture plus the number k. So you're given like, let's say the Pokemon. You're given like a list of trainers, and for each one, you're given the list of Pokemon that they have, and you're given a number k. What's the algorithms problem? The algorithms problem is you have to choose exactly k trainers in an effort to get as many Pokemon as you can, but you don't double count. So like, it doesn't help you to have more than one copy. You're just trying to get as many distinct Pokemon as you can. Okay? So for example, just so we understand, let's say the input is this picture plus the number 2. You're allowed to choose 2 people. How many distinct Pokemon can you get? It's 5. The best thing is to take this orange person and this red person, and you'll get 5 distinct ones. Okay? If you take the 2 gentlemen, you'll get only 4. 1, 2, 3, 4. You don't get to double count like I got 6 in total. It's just the total number of distinct ones that you caught. Okay? So if I give you 3, how many can you get? Yeah, you can actually get all of them if you take everybody but Ash. On the other hand, if I give you 1, you should just take one of the 2 gentlemen. You'll get 3. Okay, so is the problem clear? I'll have another example, I think, on the next slide. OK, well, it's a fact that this problem is NP-hard. I mean, if I give you this problem, finding the best team of k that maximizes the number of Pokemon you get, distinct Pokemon, is NP-hard. So we could try to find an approximation algorithm. And again, the task there, you want a polynomial time algorithm. It always chooses exactly k trainers, and it gets as many distinct Pokemon as it can. Maybe not the most, but hopefully a large fraction of the most. Okay, this is a maximization problem, unlike vertex cover, which is a minimization problem. Here you want a larger solution. So one thing you could do, I mean, if I locked you in a room and I was like, come up with an algorithm, you have 3 minutes to prepare, you'd be like, I'll try the greedy algorithm again. What are you going to do? So it's even simpler here, right? Oh, it's simple. This would literally be an algorithm you try. Just for I equals 1 to k, you have to choose literally exactly k trainers. Just pick the one that brings you in the most new Pokemon that you don't already have. So for example, again, on step 1, you'll pick the person that has the most Pokemon. But then in step 2, it depends on like how many new Pokemon you're getting. So here's an example with k equals 3. OK, here there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 18, 27, 30 Pokemon. OK? And here I have 6 trainers illustrated with colors. And k equals 3. So what do you think? If you get 3 trainers, what's the most Pokemon you can get? You cannot get all of them. Yeah, you can get 27. The best thing for you to do is take all these whitish, grayish trainers. And you'll get 27. You won't get these 3 down here. Yeah. But what will Greedy do? Well, Greedy will start out by, first take the person that has the most. And if you look, this yellow person has 3, 6, 9, 10, which is better than any of these horizontal 9s. So you'll take the yellow one. And now, having taken the yellow one, what do you do next? Well, any one of these horizontal white grayish ones will give you 1, 2, 3, 4, 5, 6 more. But this blue one will give you 7 more. So you'll take the blue one. And then you have 1 trainer left, and it doesn't really matter. Like the white or gray ones give you 4. The red one also gives you 4. It doesn't really matter. Let's say you take all the colored ones, and you'll get only 21. OK, so Greedy was not so awesome there. And you could say Greedy is at best 77.7 repeating % approximation, because 21 is only 7/9 of 27. Okay, so again, we found a specific example where it doesn't do so well. Let's do one more poll. The other poll was about calculation. This one is kind of for fun, just a guess. I mean, it's just take a guess. Wait, where is it? Here we go. So just take a guess. How good is this greedy approximation algorithm? So at best, it's 77.7%. Maybe it has a guarantee it always gets you at least 75%. Maybe it always gets you at least 2/3. Something like 50%. Maybe it's quite bad. Maybe it's like greedy, like it doesn't even give you 1%. Without having played around with it, there's no way for you to know. But I don't know, just do a guess. Prove you were here. Let's take a look. All right, yeah, I mean, there's a lot of possibilities. You could just guess. This is kind of like guessing that it's similar to, for Vertex-Cover, it's not doing very well. We got like some range of possibilities here. I'll close the poll. I'll actually tell you the correct answer. The correct answer is actually these 25 people that said between 50 and 66%. Very good if you guessed that. That's funny. So here, greed is actually pretty good. It's actually a 63% approximation algorithm. It's actually not even 63. 63% is like that 0.87856. There's a secret here. This is actually 1 minus 1 over e, where e is, that 2.718 blah, blah, blah. And that's already kind of funny, right? Like this is like a 2-line algorithm. It's a very simple problem. It's got Pokemon, and yet somehow, like e comes into the answer. It's very funny. There's the proof. I'm actually not going to read it or go over it, but you can if you're interested. It'll be on the slides. The reason I put this up is just to show you it's not that hard. It's a little bit hard, but if you make the font size small enough, it fits onto one slide. So this is a proof that it gets, and you'll see how E enters into it if you want. OK, so that's the Pokemon, the coverage problem, 63%. So that's funny. I mean, I put that in as an illustration of, I mean, how every problem is kind of different, right? Like we tried the greedy algorithm for Vertex-Cover, it was horrible. We tried the greedy algorithm for, K coverage, it was pretty good. So I mean, everything is, different. Even though they're both NP hard, the situation is kind of different. OK, last one I want to talk about is TSP. So TSP stands for Traveling Salesperson Problem. I still might say TSP problem, nevertheless, later, like ATM machine. There are many variants of it. So I'm going to focus on one, which I think is the most natural one. The nerds call it metric TSP, but let me just tell you what it is. The input is a graph, and each graph also has a cost on it. You can think of it as like the length of the edge if you want. And what do you have to output? You have to output a tour. This is a walk that visits each vertex at least once. So you're actually allowed to repeat vertices, but you just have to hit every vertex at least once. And you have to start and end at the same vertex. So like the story is you're a traveling salesperson, whatever that is, and you have to visit a bunch of cities, and you have to visit every city at least once, and you have to come back to your home city at the end. And of course, what are you trying to do? You're trying to find the route that has the least cost, the least length. OK, this problem is NP hard, by the way. But let's see what we can do. So here's an example graph that might be the input. And it looks actually a bit harder than the other problems. Like even before with that 33 vertex graph or Vertex-Cover, like you all more or less figured out the size of the smallest Vertex-Cover. It's actually a little bit tricky. If I have to find the smallest tour, the shortest tour that goes through all these vertices, like it took me a while even to do it. I mean, one thing you can do, there's only 7 vertices, so there are only sort of like 7 factorial different orderings, and you can just try them all and see which is the best. In fact, I just wrote code that did that. 7 factorial is not that large, but n factorial is very large, so you cannot do that. Anyway, the cheapest tour for this one looks like this. Start at B, go to V, that takes 3, go to S, it's 5, go back to V, go to K, go to H, go to Z, go to B. You still got to do T, so just go to T and come back, and that's it. So the cheapest tour for this instance happens to be 71. You don't have to take my word for it. OK, any questions about the problem? Yeah.
So is this probably an NP?
Is this probably an NP? Yeah. I mean, it's not technically because this whole optimization versus decision. The decision version of this is I give you a graph with the labels, and I give you a number k, and I ask you, is there a tour that visits all the vertices and has length, total length at most k? And that's.
How do you actually prove that is an NP?
How do you prove that's in an NP? The verifier expects to get the tour. And what it does to check it is it checks first that it's a valid tour, that it only follows edges, that it starts and ends at the same place, and that it visits every vertex. And it adds up all the costs along that tour and compares it to k. And if it's less than or equal to k, then it says, yes, you have given me a valid certificate. Otherwise, it rejects. OK. So TSP is actually probably the most famous NP-complete problem. Like if you read like a newspaper article that's about theoretical computer science, and they're trying to like implicitly tell the reader about NP-completeness without exactly saying it, they'll probably talk about TSP. Okay, and because that's inspired many things. For example, textbooks. For example, this is a well-known textbook called The Traveling Salesman Problem. It's literally a whole textbook just about TSP. Actually, there are many textbooks that are just about TSP. Here are 4 textbooks that are just about TSP. It's also inspired popular books, popularizations of what is theoretical computer science. So this actually got a nice book called In Pursuit of the Traveling Salesman by Bill Cook. It's motivated by TSP. Museum exhibits. So like this is a museum exhibit where like you're given like a bunch of points, like these are cities in a country, and you're given like a string that has length equal to the minimum tour through all these points, and you have to try to like wind it around the cities so that you cover all the cities in the shortest possible way. There's a Pokemon enthusiast trying to solve it. Movies. So this movie, it looks like it's called Peebles NP, but it's actually called Traveling Salesman. Yeah, here's a pro tip. Don't watch this movie. OK? Okay. Okay, well, that was a mistake. You'll never get the time back. There's another movie that's actually kind of about theoretical computer science, like a very old one called Sneakers, which is, they don't say it, but it's about people that develop an efficient algorithm for factoring, which we'll talk about later in the course. That one's pretty good. It's inspired like a 60s sitcom-themed household good conglomerate ad contests. So this is a real thing. This is from the 60s. There was a television show called Car 54, Where Are You? And they literally, this is a contest. They give you this map. It's got like cities in the US, and the costs are literally just, you get your ruler and you measure the distance between them. And the contest is to find the shortest path that goes through all the cities. There's like 33 of them. It even tells you should start like this, going through from Chicago to Erie or whatever. And you can win $10,000 back then if you find the minimum TSP solution. Okay, and actually people literally genuinely want to solve this. I mean, it's not just like jokes with contests or whatever. Like, I mean, I just Googled like, TSP, like, and I got serious papers that were like solving it, trying to solve it, about like school bus routing and, I don't know, genome sequencing and all this other stuff. And it's an NP hard problem, but they're like, well, we want to solve it. I mean, we want to do the best thing. So this is sort of in the spirit of like, you should never give up. Like, I mean, you got to come up with some algorithm that does something. And coming up with an approximation algorithm, like we've talked about, is a reasonable idea. You'll have an efficient algorithm that, for every graph, maybe it can deliver you a traveling salesperson tour. That's at most, well, it's not much bigger than the shortest one. And people have good ideas about this, and there's research on how to do this. And here's an example of an approximation algorithm for it. This is not the best one, but it's a pretty good one. It's called the MST heuristic. It's quite simple. This is the whole algorithm. You're given G. First thing you do is you compute a minimum spanning tree for G, rooted at any vertex set. It doesn't matter. Okay, and we saw in lecture 11 how to do this in polynomial time. And then once you have the minimum spanning tree, it's not a tour, but you just start from the root and do a DFS. And as you'll see, that gives you a tour. That's the whole algorithm. Let me do it in a picture. So here's this graph again. And first we find the minimum spanning tree. You all hopefully know how to do that. And in that case, it's these blue edges. And it has a certain cost, but it's not a tour. But step 2 is DFS. So let's say you start at B. And you do a DFS. So you go to V, go to S, come back, go to K, come back, go back up to B, go to Z, go to H, come back, go back up to B, go to T, come back to B. Okay. So okay, I won't exactly prove everything, but this always gives you a valid tour. I mean, you cover all the vertices, because the spanning tree touches all the vertices, and then you traverse the whole spanning tree in your DFS. So you indeed start at the root, visit every vertex, and come back to the root. Is it polynomial time? Yes, because we know how to find the minimum spanning tree in polynomial time. We know how to do a DFS in polynomial time, so that's fine. Okay, and what is the cost? Well, let me ask you this. How does the cost of the tour relate to the cost of the spanning tree? Yeah, it's literally exactly double the MST cost always. I mean, you can see it from this picture, right? You traverse every edge of the minimum spanning tree exactly twice. Okay, but we're not trying to compare this tour's cost to the MST cost. We're trying to compare it to the cost of the cheapest tour that visits all the cities. In this case, it happened to be 84, I guess, which is pretty good. The cheapest tour is 71. Here's a theorem. This MST heuristic is a factor 2 approximation. And the key claim is just that the optimal TSP cost, whatever it is at least the cheapest MS spanning tree cost. Can somebody say why that is? Well, like if you're trying to find a cheap tour that visits all the vertices, you can never beat the MST cost. Well, let's see why that is. Well, first, once we have that, then we know that proves the theorem, because the MST heuristic cost is twice the MST cost. So that proves it. Here's the claim. Let's consider the optimal TSP tour, whatever it is. It's some tour that visits all the vertices. It's actually kind of a directed tour. But just take all the edges that appear on this tour in either direction. Just take all of them. Well, they form a connected graph on the vertices. It's just like a subgraph because you've taken some of the edges. And it's a connected graph because it came from a tour, and like the traveling salesperson doesn't jump around. And it touches all the vertices because by definition it's a TSP tour. It has to touch all the vertices. So it's a connected graph on all v vertices. But it might not be a tree. It could have some cycles in it. But anyway, you can just take away some edges until it's a tree. Just make it minimal. Take away edges, maintaining that it's a connected graph touching everything, until you can't do it anymore, and then you'll have a tree. I mean, this is what we discussed in lectures 10 and 11. So you'll eventually get a tree that spans the graph, and you've started with that TSP cost, and you've only deleted some edges, so like that can only make the cost go down. Okay, so that's it. So whatever a optimal TSP tour costs, there's always a spanning tree that has a cost which is at most that. Okay, any questions about this? Okay, great. So that was a factor 2 approximation for TSP. And one thing we should always do in algorithm design is ask ourselves, can we do better than this? Can we get a better algorithm? And in this case, we can. So this is a famous result also from 40 years ago. This is proven by Christophides, who was actually a faculty member at Tepper at the time. And he gave a polynomial time algorithm that, for this TSP problem, that always finds a tour that's at most 1.5 times bigger than the optimal one. It's at most 50% bigger than the shortest tour. And that's a really great algorithm. It's pretty cool. It's not too hard. The ingredients in this algorithm are the MST heuristic goes into it. Something about Eulerian tours, which we mentioned very briefly in one lecture, like 8 or 9. And it uses there's an algorithm for finding the cheapest perfect matching in a graph. That can be done in polynomial time. It puts all this stuff together, and somehow it has this property. So it's a bit of a complicated algorithm. If I wanted to explain it to you, it would probably take one full lecture, which we won't do. But it's a nice algorithm. It has this very nice guarantee. Its solution is at most 50% bigger than the shortest TSP solution. And actually, there's been no improvement on that in 40 years. So that's the best thing that's known. However, there's a special case of TSP, which is pretty natural, and where we can do a lot better. The special case, the official name is Euclidean TSP, but it's the case that was kind of like in that Car 54, Where Are You advertisement, where the graph is just points, like literally on the plane, like on a piece of paper, and the edges are not just some arbitrary cost, but it's literally just the distance, like the normal distance, straight line distance between the vertices. That's a special case. Like the vertices are on a piece of paper, and the distances are not arbitrary. It's just literally the usual distance. This special case is actually still NP-hard. Even though it's a special case, it's still NP-hard. But there are even better approximation algorithms for it. So in 1998, these two people, Aurora and Mitchell, not working together, but actually working separately at the same time, they came up with an approximation algorithm that guarantees a 1.3 factor approximation for TSP. So it's never worse than 30% larger than the shortest TSP tour. Actually, it's a little better than that. I mean, I wrote 1.3, which is true, but it's actually something even better is true. It's actually a 1.1 factor approximation algorithm. So it's actually never more than 10% worse than the optimal solution. Actually, something even better is true. It's actually a factor 1.01 approximation algorithm. They can give you a polynomial time algorithm that finds a solution that's never more than 1% longer than the optimal solution. That's pretty good, right? I mean, at that point, you should just be like, all right, that's good enough, right? 1% better than optimal is pretty good. Although they didn't stop. I mean, it's also factor 1.001. So it's like they have a polynomial time algorithm that's at most 1/10 of 1% worse than the optimal solution. So it's like, even though it's NP-hard, like basically it's not NP-hard. I mean, you can get almost the optimal solution in polynomial time. It's actually even this one, 1.0001 approximation algorithm. Something sounds funny about the way I'm telling you this, right? I mean, what's going on here? There's actually a catch. There's a catch. Can anybody guess what the catch is? Yes, it kind of can get arbitrarily close, but I mean, let's say the person in the light blue shirt.
You run more iterations to get closer approximations, so it takes longer.
Yeah, that's right. The running time gets worse, slower, the smaller you want this number. So like, you can put any number here you want, like 1.01, and there'll be a polynomial time algorithm, but like, it'll be slower than the one for 1.1 factor. And like the one for 1.001 will be slower, but still polynomial time, than the one that got you 1.001. In fact, the running time is something like this. So it's true that for any positive number epsilon, they have a polynomial time algorithm that always gives you a solution that's at most 1 plus epsilon times the length of the best solution. And the running time is something like n times log n to the power of 1 over epsilon. Something like that. So it's actually not so bad. I don't know. I mean, if you take epsilon to be a half, then this becomes 1.5, and it's something like n to the n times log squared n time. Or if epsilon is 0.1, it's like order of n times log n to the 10th time. So for any fixed epsilon, that's still polynomial time. Now, OK, if you really want 0.0001, then this will be some enormous power, and so maybe it's polynomial time only in theory. But actually, in practice, it's also good. So, as I said, even though this problem is NP hard, in some sense, it's really not that hard. And indeed, people just solve it. So this is an example of the solution, the optimal solution, actually, to a TSP instance with like about 10,000 vertices. They're all towns in a certain country. Anybody say what country this is? Sweden, thank you. It's Sweden, that's right. You got the islands here. Yeah, I think it's Sweden. Yeah, so they put like 10,000 towns in Sweden, and they use just the normal straight line distances between them, and they can actually find the optimal solution with a heuristic that runs, in not too long a time. So that kind of illustrates that theory is a bit matching up with practice here, in the sense that it's really, people can solve Euclidean TSP basically optimally, efficiently, even though technically it's NP hard to find literally the optimal solution for every possible graph. OK. Good. So we saw actually 4 approximation algorithms in the end for Vertex-Cover, K-coverage, TSP, and then the special case of Euclidean TSP. And they had different approximation factors. And as I said, we should always ask ourselves, can we do better? Maybe, we got a factor 2 approximation for Vertex-Cover. Maybe we can get a factor 1.5 algorithm for Vertex-Cover. Well, I'll tell you about the story for each of these 4 problems. And I'll tell you in a reverse order about whether or not we can do better. So I'll start with 4 and go back to 1. OK, so first one. Can we do better than this? Well, what more do you want? I mean, that's about as good as it gets. I mean, it's de facto easy problem. OK, so that's that. OK, what about TSP? Just the general case, where we have this Christophanides from Tepper 1.5 factor approximation algorithm. Can we do better than that? Well, on one hand, as I mentioned, in 40 years, nobody has been able to do better than that. However, I would say if you actually poll experts in this area, like if you ask, let's say, Professor Anupam Gupta, who works on stuff like this, what do you think? I think he and many other people will say, actually, we expect that you can do better. We expect that in polynomial time you can beat this 1.5. And probably the reason for that is it's actually been studied. I mean, there's been a lot of new ideas, kind of breakthroughs in the study of TSP over the last 5 years, approximation algorithms for TSP. I mean, they haven't literally beaten this, but they've beaten it in a lot of special cases. They have a lot of interesting new ideas for algorithms for TSP. They've really had a lot of progress. I mean, it's a hot area. And in light of this, I mean, I think they're going to make progress on this 40-year-old problem pretty soon. Like I personally, let's say, will bet that come back in 10 years, I'll have to change these slides because I think they'll get it better than 1.5. It's just a guess, but that's what I think. As I said, it's like an area that has a lot of active research, approximation algorithms. OK, let's go back to this Pokemon problem, the K-coverage problem, where we got the 63% approximation You always found k trainers that got at least 63% or even 1 minus 1 over e factor of the best solution. Can we do better than this? No, we cannot. Well, I can't say that definitively, but what I can say is it's not possible to do better than this unless p equals np, which basically no one believes. Why do I say that? This theorem is true. Doing better than this is np hard. That's a theorem. We'll just explain what that means. For this to be np hard, take any number that's bigger than beta, that's bigger than 1 minus 1 over e, like 0.64. And ask yourself, is there a polynomial time algorithm for this Pokemon problem that for every input always finds a solution that's at least 64% as large? Remember, you're trying to get more in this problem. 64% as large as the optimal solution. Can we do that task, getting 64% in polynomial time? Well, this person Feiga in 1998 proved a theorem that says if you had an algorithm like that, you could use it as a subroutine, as an oracle for solving SAT in polynomial time. I.e., it's NP hard. Somehow you could convert this like 64% solver for the Pokemon into an algorithm that solved SAT in polynomial time. And it's literally just an NP hardness reduction like you're doing in your homework and you'll do on the midterm and you'll do on the final. It's just an NP hardness reduction. There's one difference, which is that it builds on many, many prior works. And if you were to look at like the length of this reduction in proof, it would be like 100 pages long. Okay, so you will not be proving things like that on your homework or whatnot. But in spirit, it's the same thing. It's just a really long NP hardness reduction given 3 SAT or SAT instance. You solve it by imagining you have an oracle that does 64% on this Pokemon problem. And it's not even 64%. It's literally this 1 minus 1 over e. So in fact, it's kind of amazing. Like this is sort of the best approximation algorithm for k coverage, assuming p does not equal np. OK, last one, Vertex-Cover, where we had this Gavril factor 2 approximation algorithm, also from 76. This one we have no idea if we can do better. There's a theorem that's kind of like the Feiga theorem, but it's not as good. It's proved by Irit Tenur and Muli Safra in 2002. Irit Tenur is like my hero in theoretical computer science. She has all the coolest results, including this one. They show that it's NP hard to get more than 1.36 factor. It's actually like 10 root 5 minus 21. It's a very difficult paper. It's in Annals of Math. It's probably actually my favorite research paper of all time. I can't really explain why, but it's got like 2 totally amazing ideas in it. And so this gives you some state of affairs. It says, trying to get small vertex covers. There's a simple algorithm that always gives you one that's at most twice as good as optimal. And they're telling you that there's no algorithm in polynomial time that can always guarantee you at most 36% better than optimal. But what about in the middle? Somehow, like this is the picture. Let me just click through all these. If the factor is ranging like this, Gavril says once the factor is above 2, he can do that in polynomial time. It's NP hard to get the exact optimal solution. That's like a factor 1 approximation algorithm. And Tenur and Safra said it's even NP hard to get at most 36% worse than the optimal. And in here, we actually don't know. Not only do we know, unlike with TSP, where if you polled researchers, they'd say, we can probably get a better algorithm. Here, if you polled researchers, I think you would get like a 50-50 split. It's actually kind of controversial. Like, oh yeah, I have office hours in 5 minutes, by the way. Should be 10 minutes, though. Anyway, yeah, so it's like a raging controversy among computer science theorists. Maybe I'll tell you about it another day. OK, so see you next time.